Welcome back, and in this video we're going to go over the area beneath a curve. So this is a big part of the integral calculus units. We're going to just quickly look at the fundamental theorem of calculus, so how these three things are linked, and then I'm basically going to go through a series of examples where they are all definite integrals and we have to find the area beneath the curve in each one. Now some of them involve reciprocal functions and some of them will involve logs and exponentials. So I'll go through those. This is part one of the video, and in part two I'll go through some more complicated examples where the curve crosses over the x-axis and we'll be asked to find areas involving positive and negative areas and how we'll deal with those. Okay, let's dive in. Okay, so the fundamental theorem of calculus sounds a little bit complicated, but really it's just a link between these three sort of scenarios. So when we have a integral and there are limits known as a definite integral, we will end up with a antiderivative. So sometimes what it's better to look at it like this is if this is differentiable, okay, and then we will be able to get f of x. And if we go the other way and it is integratable and it is continuous, therefore no breaks in the curve whatsoever, like no asymptotes, then we'll be able to get back to f of x. So these two switch between each other like that. Now, when we have limits like the definite integral a and b on here, then we will put limits on our integrand or our antiderivative. B will be the upper limit and a will be the lower limit, and we will substitute b into this expression first, and then we will subtract the value that when we substitute a into that. So when we do all of that process, we'll end up with what we have up here on the right. So we will find the area beneath the curve and the x-axis. Okay, so on to our first three examples here. Find the area bound between the curve y and the x-axis. So in this question here, it says find it between 0 and 1. So what we'll do is we'll set up the problem in the following way. We'll say that the area can be found by doing the definite integral between 0 and 1 of x squared dx. Now what we want to do is we want to integrate this, and so therefore we'll use this sort of reverse power rule. So we're going to add 1 to the power and divide by the new power. But then we go ahead and we put our square brackets on. And this is important because we need to put our limits on 1, 0. So this will work out like the following. So we plug 1 in, so that'd be 1 cubed is 1 over 3. Then we subtract when we substitute the lower limit in. Now when we plug that in, we will just get 0. So the answer to this question is the area beneath the curve is 1/3 units squared. Now we don't know what the units are on this, so we'll just leave them as units squared. So this, just to be absolutely clear, this area here that I've just shaded in yellow is 1/3 units squared. Let's go over to B. So we want to do the same thing here. This time we've got a square root or a radical, and it's between 1 and 9. So we're going to set this problem up here that the area can be found by doing the integral between 1 and 9. Now I won't write the square root of x. I will write it like x to the power of a half dx, because I want to be able to integrate that using the sort of reverse power rule. So when we do that, I will add 1 to the power. So we'll get 3 over 2 dividing by the new power. That's the same as timesing 3 by 2 over 3. Don't forget your square brackets. And therefore now we need to put our limits in, which are 9 and 1. So we always put the upper limit at the top and the lower limit at the bottom. We now need to substitute this in. So what might be helpful now is that we unpack the power, because we're going to do this without a calculator. So we'll have 2/3, then you can rewrite this as like x to the half, then cubed, right, all raised to the power of 9, sorry, to the limits 9, 1, and therefore then when we substitute 9 into this, we'll have 2/3, and it will be root 9, because remember this expression here, this x to the half is the square root, so it'll be root 9, then cubed, and that'll be the first term. Subtract, and now we want to plug 1 into this, so we have 2/3, and it'll be 1 or root 1 and then cubed, and we'll just close that off. So we're just plugging them independently. I should be able to do this pretty easily. So the 2/3, then we have the square root of 9, which is 3, 3 cubed, which is 27, subtract 2/3, and then root 1, then cubed is just going to be 1. So therefore, 27 divided by 3 is 9. 9 times 2 is 18, and then we have to minus 2/3. So we'll end up with 17 1/3 units squared, and that's the answer for the second one. Let's go over to this one here. So this is between 1 and 4, and it is a 1 divided by. So what we'll do first of all is we'll write this as x to the minus half. Okay, we haven't done any integration there. We've just used our rules of indices to tidy that up. So we've got the area is the integral of x to the minus half, and the limits that go onto this will be 1 and 4 this time. And when we add 1 to the power, we will get x to the half, right? Which is actually the square root of x. Don't forget your square brackets and your limits, which are 4 and 1. Now, we know that the square root of something is also known as to the power of a half. So therefore, then we're going to just go down here. So this is basically saying the square root of 4 minus the square root of 1, which is going to be 2 subtract 1 equals 1 unit squared for area. On to the next two examples. So this time we are going to end up with a natural log when we're working on D. So let's focus on D just to begin with. So it's asking us to find the area between 1 and 4. Right, well, the area is governed by the integral between 1 and 4 of 2 over 1 plus 2x dx. Now, I'll put the link into my description how to integrate a reciprocal like this, because it will end up in a natural log. So therefore, then this will what you can do is you can move the 2 outside, and then you can say between 4 and 1 of 1 over 1 plus 2x, because that is the same expression. If you times 2 by the numerator here, you'll get 2. So that is the same. But then when we have that, I'll just put the dx on. When we have that, then we'll get 2 square bracket natural log 1 plus 2x close bracket divided by the derivative of this power here, and the derivative of that power is 2. So therefore, then that'll be 2 here, and then we have our integral close bracket and 4 to 1. So 4 to 1. So we want to substitute everything into this now. So we're going to get 2 times, and what I'll do is we're going to plug 4 in to begin with. So 4 is going to come in into all of this. So we're going to have half natural log, and then 1, so that'll be natural log 5 because we plug 4 in. Subtract a half, and then we'll have natural log, and we plug 1 into this now, we'll get natural log 3. So natural log 3. And you can see, obviously, a factor of half could come out of this, resulting in 1, open brackets, natural log 5 minus natural log 3. And we can use laws of logs there to divide. So we'll get 1 over natural log 5 divided by 3, close brackets, and obviously that we don't need the 1, so that will all break down into just natural log 5 over 3 units squared. Going up to E here, what we can do now is this is between 1 and 2. When we integrate this, we will end up with the integral of 1 to 2 of 2e to the 2x minus 3 with respect to x. And what I want to do is when we integrate an exponent, it stays exactly the same, but then we must divide through by the derivative of the power, and the derivative of that power is 2. So when we do that, the half times the 2 will actually cancel, resulting in 1. So that's very handy. And minus 3x, because when we integrate this, we add 1 to the power. So that will make that 3x. And then we've got our square brackets and our limits 2, 1. I will just write that just out again, just so you can just see a little bit clearer of what's going on. E to the 2x minus 3x, close brackets, 2, 1. Now let's go ahead and substitute 2 and 1 into this. So when we substitute 2 in, we will get e to the 4 minus 6 close bracket. So remember, you have to plug it into both of those. And then minus, and we plug 1 into this, it'll be e squared minus 3. Now, there's only a little bit of tidying that can be done, and that will be with these sort of integers here. So e to the 4, subtract e squared. We can't do much about that. But minus 6 minus minus 3 is minus 6 plus 3. So that would be minus 3. And that's our final answer, units squared. And that is the area for that question. Okay, on to this example. So what happens when we have an area beneath the x-axis? Well, it does say find the area bound between the curve and the x-axis. Now, area is like a scalar. It's always going to be positive, because if you're finding the area of any object, it has an area. It doesn't matter if it's above or below the x-axis, it still has an area. So we won't put negative on this result. That's quite important, and I'll cover that more in video 2. So please watch that. So if you were not told, well, they've shown us what the intercepts are here. So it's going to be so the area is between -3 to 0. I can actually see that just by factorizing this out and looking at when it equals 0. I can see that straight away. But it passes through 0, and this is x squared plus 3x with respect to dx. And so what we'll do is we'll do what we've done on the previous ones. We'll add 1 to the power and divide by the new power, add 1 to the power, divide by the new power, put it in square brackets, and then we need to put our limits on. Now, just be careful here. Your upper limit is still the largest number on the number line with respect to the other. So 0 is bigger than -3. So 0 to -3 there. And then we plug 0 into this. That first expression is going to come out to be 0. In fact, the second expression is going to come out to be 0. Then we have minus. Let's plug -3 into this. Well, that 3 times 3 times 3 is -27 over 3. That's going to be -9. And then we have plus. Now, -3 squared is 9 times 3 is 27 over 2. Right, so just got to just sort this fraction out. Well, let's just do 27 divided by 3 is actually just 9. So let's just write down what we've got minus, and then we've got -9 in here, plus 27 over 2. And that would result in +9 subtract 27 over 2. If you want to just combine that into a single fraction, then that would be 18 over 2 subtract 27 over 2. Difference between 18 and 27 is 11, but it'd be negative over 2. And don't forget, that would be units squared. Thanks for watching. If you like what you saw, leave me a like, subscribe, hit the bell notification so you get alerted next time. Also watch part 2 of the video where I go into more complex examples with areas above and below the axis. Okay, I'll see you next time.